extending, and thermodynamics was delivered in Glasgow's year 2. So this slide serves as a review of what was taught to the students over there. But if you don't have thermodynamics background, don't worry, because this module is heat transfer, it's not thermodynamics. So what I need is to just briefly walk you through these couple of slides. They are not really very critical. It's talking about energy that's going into the system, right? The rate of that energy going into the system minus that energy that's coming out plus generation of energy within that system. It gotta be equal to the energy storage. This one refers to storage of the energy. So whatever that's the rate of energy that's going in there, that's E in, minus whatever that's coming out, the rate that's coming out, E dot out, plus the generation of energy within the system. So it could be a chemical reaction that's going on in there, like combustion that's going on in there. So if you have that kind of fluid flow through the system, then you would have energy, the rate of energy that's generated. So this G here refers to generated energy. So if you're wondering, then what is E dot? E dot refers to your rate of energy. It means dE dt, the rate of energy. So this law governs your first law of thermodynamics. And the formal definition is given over here. And the next slide is even more far-fetched. Talks a lot more about symbols that you've never seen before. Like this, that. You've never seen before. Right? But I just want to briefly talk about it. What it means is that if you consider gravitational potential difference, there will be kinetic energy, potential energy. So those kind of things are captured over here. Right? Enthalpy refers to the change of state. In your fluid flow, actually we don't experience, there's actually another chapter talking about change of state. But I think in your convection, you wouldn't be feeling that much about change of state of the fluid. What do I mean by that? So imagine if you have a 200 degrees Celsius pipe here, and the fluid is flowing in there, say water. You would know that after some point of time, the water will start to boil along the way, because that pipe is 200 degrees Celsius. So that pipe, that fluid, that water that's going through there would have a change of state from liquid to gaseous state. There are those heat transfer formulas relating to that kind of thing, and that's captured by your enthalpy. Right. I would also briefly mention about enthalpy when we come to your last lecture, where we talk a little bit about advanced topics. So for now, a lot of what you can see over here is actually going to sum up finally with this equation over here. That is the one that matters most. So I want to do a sketch. So in this sketch, I have this pipe here that's at a higher temperature. So if I have fluid that's flowing in there, and I know that as the fluid flows in radially, it will get heated up because my surface of the pipe here is at a higher temperature. So Q is flowing in radially. So if I enter here as a cooler temperature, say cooler temperature of T in, this T out here, you would know that is going to be higher. So T out will be greater than T in, because it gets the liquid here gets heated up. So it will gain that amount of heat. The amount of heat that it gains as it flows through is actually equal to the amount of heat that you put in radially into the fluid. So later on, you get to see that we need to equate these two equations. One of it would be the heat that's transferring in, and transferring in here, it could be via convection. Because your convection is where heat can get transferred from the solid to the liquid, or the fluid over here. So that heat that's transferring in via convection, that heat Q, got to be equal to the heat that it gains after it passes through from the inlet point to the outlet point. So that heat Q that it gains as it passes through that is actually equal to m dot Cp and T out minus T in. That's given by this equation over here. So that's to say this Q will be equal to my Q convection that's going into there. These two Q, they will be equal to each other, provided that your pipe has got thermal insulation. Now that's a part that I need you to know, right? And this is an important concept. A lot of times it comes up in exams and just keep on testing you that same thing. That do you understand that if you have a heated pipe, that liquid flows through it, that liquid will gain that heat transfer rate, and that's actually equal to the convection that's going in. So this is the equation that I need you to memorize. Right? It's not going to be provided. So please know this equation. The next few slides went about deriving a lot of other things. So I'm going to walk you through. Hopefully, okay, it's only about 4 slides, right? Only about 4 slides. It can be 4 big slides. Let's have a look. So just now I said this is T in and there's T out. I'm going to relabel them. There's TMO and TMI. Sorry, the other one. This is O and this is I. I refers to inlet. O refers to your outlet. M here refers to the mean temperature. So your mean temperature that's coming in for the inlet, the mean temperature that's exiting the outlet. So for low speed flow, where this velocity that's flowing in there that's less than c, this c refers to the speed of sound. Right? So if that's the case, then based on what we had before, this equation over there, where Q convection is equal to your mass flow rate multiplied by Cp, and the temperature difference between the outlet and the inlet. Right. So over there, it's not written as a convection, right? But we know that if this wall here were to be hot, then it's actually convective heat transfer that's going to be happening as the fluid moves along. So the following are the definitions of all the various parameters over there. And what I want to emphasize is on this element over here. Right? If I were to look at this element, you have the temperature difference between the two sides. Now obviously, your fluid flow that's going in there over on this surface is going to have Tm as my mean temperature. And this is a very thin slice of dx. So at dx distance away, that Tm here is going to gain a little bit more temperature. So I plus dTm over there. Okay. So if you look at just this slice over here, what it is that this is kind of over here is your inlet, and over there is going to be your outlet. So what I have from this equation, there will be m dot Cp. My outlet would be Tm plus dTm, and my inlet will be Tm, or if I were to put inlet and outlet, no, I don't. So Tm over there. So if I were to solve it, this and this would cancel out, and I'll get m dot Cp dTm, and that's this equation that's given over here. Okay. So that's to say this part here is actually my Tm inlet. That part here is my Tm outlet. Now there's also this part here that I didn't explain, this top part over there, where we talked about the convection that's going in it. So you can see that is equal to the following form for convection. Now that double prime means that it's per unit area. So that Qs double prime multiplied by P. P here is your surface parameter. And dx here is the thickness of that slice. So if you look at it, this is kind of like your surface area where heat is transferring radially into it. So this whole thing is your surface area where heat is transferring perpendicularly into the fluid. Okay? So we can call this as dA. So if I were to break it down, that is Qs double prime pi d dx. That parameter is actually pi d. This parameter is your 2 pi r. So 2 pi r is actually equal to your pi d, where d is your diameter. The diameter d over here. So this part over here is sort of like your dA, where dA is that shaded part that I have over here. It's going all around it here. And that circumference, all around it, that is your dA. dA. So that will be equal to, if you take that Q double prime multiplied by dA, you get the Q convection. So heat is transferring in radially because that surface is hot. So I'm going to try to solve this one in the red box. So the one in the red box, I'm going to bring it out somewhere over here. So that the Q convection is equal to Qs double prime P dx. That one must be equal to the mass flow rate that's going in there, multiplied by Cp, multiplied by dTm. Right? So whatever convection, heat transfer going into the fluid must be whatever that heat that is gained as the fluid flows through the pipe. That's why these two equations are equated together. So I can now solve that. That is bringing this dTm to one side. I have that dx, bring it to the other side. And the rest of it is Qs double prime P divided by m dot Cp. So this can be equated equal to P divided by m dot Cp. And this Qs double prime is our Newton's law. That's H Ts minus Tm. And this under the assumption that Ts is greater than Tm. If Tm is greater than Ts, then you just put Tm minus Ts over there. So that's how we get to this equation over here. I also want to prove this equation, this set of equations over there. So maybe I'll just write it underneath it. Okay. So this one says that I'm going to start by integrating this equation. I'm going to start by integrating this equation. Integrating the Tm over the x equal to integrating that Qs double prime T divided by m dot Cp. Right? Integrating that. So integrating Tm, the Tm over the x, I'll get Tmx. Right? And integrating this part over here, I'll get Qs double prime T over m dot Cp x plus the constant C. So in order to solve the constant C, I need the boundary condition. The boundary condition would be Tm at 0, and this 0 here refers to x equal to 0. When x is equal to 0, your Tm will be equal to 0 as well. So if you're to substitute that in, substituting into this equation above, that means your Tm Tm0 is actually equal to 0. Is actually equal to Tm over here because x refers to the inlet, right? And the inlet, your Tm is actually equal to Tm. That's where you have your temperature that's coming in. This is at Tm. So if you're to substitute that in, you get Tm is equal to Qs double prime P m dot Cp at x equal to 0 plus C. So that means your C will be equal to Tm naught. So if I were to substitute now that C term inside it, I will get, therefore, my Tmx equal to Qs double prime P over m dot Cp x plus Tm, I think it's I, right? This one is the inlet. Thank you. That one will be I. Right? Because that's the inlet. Insert that. So that's how we got to this form of the equation. And this is the one that tells us what is our temperature. This is our temperature profile. This is our temperature profile. So there's still a little bit more, so I need to go through them. So for a constant surface temperature, we define that Ts minus Tm as delta T. Ts minus Tm, that's coming from this part over here, that Ts minus Tm. We're going to let it equal to delta T. And this dTm over dx would have a negative gradient of that temperature drop across that distance. So this one is a negative gradient. And that's why there's a minus sign over there. And my dTm over dx is actually equal to this. So that was what we saw before, where we let this part here be equal to delta T. Right? So the next thing is to make use of this equation over here, this one and that one, using the mathematics technique, separating the variables. Right. If you're not familiar with separating the variables, no problem, I'll walk you through. In order to separate the variables, you could see that that dx can be moved to the right-hand side. So what essentially I'm doing from this step over here, minus the delta t over dx equal to p over m dot cp h delta t, is to separate this variable over here in the following way. I'll have the delta t that stays and bring this delta t to the left-hand side. This part here is all going to stay. So I have p over m dot cp, and the h is going to stay there. And I'm going to bring that dx over the other side. And I'll have a negative sign over there. What I'm going to do next is to integrate both sides. Integrate from delta t I to delta t naught. And respectively, over here, because p, m dot cp, they are all constants, so I can take it out from my integral. And I'll integrate this h, which is a local heat transfer coefficient, integrate from 0 to L, where L here refers to the length of the pipe. Okay. And that's how we got to this expression over there. So if I look at this, integrating the delta t over delta t, in order to integrate this is very similar to integrating 1 over x dx. So integrating 1 over x dx, you get ln x. Right? So this is kind of like in a short form, in a shorthand, it's written as integrating dx x. So it's very similar to this. Very similar to that. So if I were to integrate that, what I get is ln delta t, and if I were to substitute the limits in there, minus delta t I. And integrating on the other side, minus p over m dot cp. And what I'm going to do is to introduce another variable, L multiplied by 1 over L. And I'm going to make use of this and bring it into my integral expression. Okay? So ln minus ln, you can compress it, delta t naught over delta ti. And then this part over here, the constant is going to stay. And then this is where we call, this is our HL bar, the average heat transfer coefficient along the length of the pipe. So that is the part that we are trying to go after. So now that we have this, in order to express this part, inverse ln on both sides, that will give us e to the power minus pl over m dot cp. And this L over there, we can start to ignore it because we know that this is average. So average got to be over the average length of the pipe. So we can just write H bar in that following way. So that is where we come to this equation over here. Okay. Now you see that this equation has this term over here. That's because delta T naught is actually Ts minus Tm naught. And delta Ti is actually Ts minus Tmi. Right? That's the definition of delta T naught and delta Ti. So generally, we can then start to write it in the following form. Now this form is very similar to the form above, except that for your Tm naught, we express it as any distance Tm at any distance x. And this Tmi remains over there. So this expression is what we'll be using in our example questions later. Now note that this h bar is actually the average of the local, this is h here, that's your local heat transfer coefficient. So we need to have an expression to cover the entire heat transfer coefficient along the entire length of the pipe. So now this is the last slide before we go into examples. So this part here, I need to come to that final expression, and I need to further develop that Q convection, which is mass flow rate multiplied by Cp, and this term over there is actually your delta Ti. It's a delta Ti. That term over there is your delta T naught. So if you were to express it in the following way, this Q convection is actually equal to your Newton's law. Right? I'm just going to help you to find out what is your delta T Lm, what is that about. So because we know that ln delta T naught over delta Ti is equal to minus PL over m dot Cp h bar. And that's coming from the Earth. I can re-express this by having m dot Cp in the following way. Just re-expressing this is minus PL h bar over ln delta T naught over delta Ti. Alright, just re-expressing it. What I want to do is to substitute this term, m dot Cp, into here. So if I were to do that, that means my Q convex, that is m dot Cp delta Ti minus delta T naught. That will be equal to replacing m dot Cp minus PL h bar over ln delta T naught over delta Ti multiplied by delta Ti minus delta T naught. This minus sign, I'm going to bring it in. So I have PL h bar. If I bring that minus sign in, that will give me delta T naught minus delta Ti divided by ln delta T naught over delta Ti. PL here, P refers to the parameter. The parameter of your pipe. That's an internal parameter of your pipe. Multiplied by the length. So that actually gives you your area. Your surface area where heat is transferring in perpendicularly. So parameter multiplied by the length. That's where heat is transferring in perpendicularly. So PL is written as AS. S refers to the surface area where heat is transferring in radially and perpendicularly into the fluid. So overall, I can write as H bar AS, and this whole term over there, I can compress it by a symbol that is delta T Lm. This Lm refers to log mean. And this whole term over here refers to the log mean temperature difference, LMT. So when we go to heat exchanger, we will get here LMT in. what is LMTD? Why do we need LMTD? And if I were to look at this expression, Q convection equal to H bar AS delta T LM. This one is log mean temperature difference. This whole thing is log mean temperature difference. What is it that is capturing that's different from Q convection? Your Q convection, Newton's law says that it's Q equal to HA, the temperature difference, delta T. That looks very similar to this one. So what is the difference here? The difference in the Newton's law is that it didn't consider that your H value would change as the fluid flows through that surface. The H value remains the same. That's why for your Newton's cooling law, this H refers to a local heat transfer coefficient. Whereas for this expression over here, because we know that the H value is going to change as it moves through your pipe, that's why we need to consider what is your inlet, and what is your outlet temperature. It's only then that the heat that we calculated would be truly the amount of heat that's transferred to the fluid. We can't use a localized H value. Right? So that's what LMTD is trying to tell us. So this is your Newton's cooling law. And this equation over here refers to the heat that's transferred by convection. It's a more realistic case of heat that's transferred into your fluid because the H value is going to change along the way. That's why we have H bar. So I think there's only time for one example. So I'll go through this example. The solution for that is only one page. And what I'll do is that I'll upload the second example solution into Moodle so that you can look at that. These two examples are actually pretty similar. Let's look at the setup. Now this setup says that steam condensing on the outer surface of a thin wall circular tube, and the tube has a certain diameter of 50 millimeters, a length of 6 meters, and it maintains at the uniform outer surface temperature of 100 degrees Celsius. So Ts on the surface is 100 degrees Celsius. The fluid that's flowing in there is water, and it has a mass flow rate of 0.25 kilograms per second. There's an inlet temperature, 15 degrees Celsius, and an outlet temperature of 57 degrees Celsius. If you take a step back, look at this question, I think those numbers make sense. You have the surface of the pipe at 100 degrees Celsius, the inlet 15 degrees Celsius, that's pretty cold water that's going in. And you would know that the exit temperature is going to be higher because heat is transferring in along the way. So that exit temperature is 57 degrees Celsius. So let's have a look at the solution. Now the solution actually requires you to look at your Holman textbook for a table that's in Appendix A9. So if you don't have that, it looks something like this. Right? Appendix A9 as a table for properties of water. And we actually need this property of the water that's coming into it at 36 degrees Celsius. So 36 is somewhere over here. And we want to find out what is CP value. So the CP value over here, 4.17, there doesn't seem to be any change. So 4.174. If there are differences, for example, in between these two values, then you need to do interpolation. Right? Do interpolation. if you have, if you don't know how to do interpolation, please look for me. So in our case, this is 36 degrees Celsius. That's my mean temperature difference. So I have 15 and 57. So my Tm mean is actually 36 degrees Celsius. And correspondingly, the CP, that will be 417, what's the other one? 4174. But in Glasgow's notes, they actually refer to another textbook's table, and that other textbook table gives 4178 joules per kilogram Kelvin. So you could refer to Holman textbook, no problem. So the question is that, then how about exam? I can't bring in Holman textbook. Well, it will be given to you in the form of table, part of the question. So that is your average temperature. So that's your table A9. So Q convex is actually equal to mass flow rate Cp Tmo outlet minus Tm inlet. That one got to be equal to your Q convex. That's H bar As over Tm. So since this is Q convex, that's Q convex, I could put these two equations together and bring out H bar as a subject. So I'm going to rearrange that formula. That will give you the following. The As is actually pi dl from this surface area where heat is transferring in radially. So that will be Tm outlet minus Tm inlet divided by delta Tm. So we know that my delta Tm delta TLm. My delta TLm is actually Ts minus Tm naught minus Ts minus Tm I divided by ln Ts minus Tm naught divided by Ts minus Tmi. So I can calculate that putting in the values. That's 100 minus 57 minus 100 minus 15 divided by ln 100 minus 57 over 100 minus 15. So if I work it out, that will give me 61.6 degrees Celsius. We stick to degrees Celsius because all these temperatures, they are in terms of degrees Celsius. So now that I have my delta TLm, my H bar here can be found out. That will be using this equation, and I'm going to put in the constants that were given. So that mass flow rate is 0.25. The CP value, that is 4178, divided by pi. Diameter is 0.05, and the length of the pipe, that is 6 meters. And Tm naught minus Tmi, that's 57 minus 15, divided by my delta Lm, that's 61.6. If you do that calculation, you get H bar